Mass 8 times that of the Sun. In this case, the star will go through another process. This star will initially perform a fusion reaction with hydrogen as fuel. After burning all the hydrogen, it will burn helium, then carbon, and finally iron. During this process, the core of the star will become hotter and denser, becoming a giant superstar. When iron is created, the star will no longer be able to perform a fusion reaction with iron because iron is too stable. Finally, when the fuel is exhausted, the core of the star will collapse rapidly due to the extremely high temperature and extremely strong gravity. The outer shell of the star will be shot out in a terrible explosion, releasing a huge amount of energy. That is a supernova. When the supernova explodes, the elements that have accumulated in the core of the star will spread throughout the universe. These heavy elements will become the raw materials to form new stars and planets in the universe. After the supernova explodes, only the core of the star remains. If the mass of this core is between 1.4 and 2.5 times the mass of the Sun, it will become a neutron star. If the mass is larger, it will become a neutron star. It will become a black hole. The diameter of the neutron star is only about 10 to 20 kilometers. However, the mass of the neutron star is larger than the Sun. The gravity of the neutron star is extremely strong enough to change the atomic structure. The core remaining after the supernova explosion is mainly made of iron, along with some other elements such as nickel and cobalt, due to the gravity and the extreme pressure. The electrons are separated from the nucleus and move freely, called free electrons. The atoms only have the nucleus in a state of complete ionization. An interesting thing happens. The pressure and the extreme gravity of the neutron star causes the free electrons to collide and combine with the nucleus, in which protons turn into neutrons, and neutrinos are released. This process continues. The electron disappears. Protons turn into neutrons, and the number of neutrons increases. Finally, heavy atoms like iron in the core stir. All turn into neutrons, creating a super-dense and super-heavy neutron star. We have learned about the process of neutron star formation. So what is Pusa? Pusa is a type of neutron star that meets the following conditions. First, it must rotate extremely fast with speeds that can reach tens to hundreds of revolutions per second. It must have an extremely strong magnetic field, emitting strong electromagnetic rays, such as radio waves, gamma rays. Third, these electromagnetic rays must be observable from Earth. When all three of these conditions are met, Pula will emit regular signals like a lighthouse guiding the Tau at sea. The reason Pusa spins fast is due to the law of conservation of angular momentum. Just like an ice skater, when pulling in his arms will spin faster. Neutron stars do the same. When a supernova explodes, the star is already spinning, and as it shrinks in size, the rotation speed increases to conserve angular momentum. NASA and ES Hubble Space Telescope was launched into orbit on the Toy Discovery spacecraft on April 24, 1990. Hubble is the first space telescope in the past 34 years since being launched into space. It has brought a new perspective on the universe, sending back data and images that have changed scientists' understanding of the universe as well as public awareness of it. Hubble's discoveries revolutionized nearly every field of current astronomical research, from planetary science to cosmology. The Hubble Deep Field and its images are truly beyond imagination. In this video, we will review some of the greatest scientific discoveries of the Hubble during its more than 3 decades of operation. The first and most memorable result is the famous Hubble Deep Field image. This is a prolonged observation of a specific area of the sky to detect faint objects by collecting light from them. Over a long enough exposure time, these images were later published and fascinated both scientists and the public when thousands of galaxies were recorded in just one single photo, causing widespread amazement and curiosity around the world. The Hubble Deep Field Scene, published in 1996, included an area of the sky only 1/12 the width of the Moon, in which the Hubble found nearly 3,000 distant galaxies, followed by the Hubble Ultra Deep Field Image, published in 2004, was the deepest portrait of the visible universe ever achieved by mankind. In 2004-2012, Hubble Extreme Deep Field Image is an impressive combination of over 2,000 exposures into one image. The resulting image has amazed astronomers by studying the thousands of galaxies recorded in these deep field observations, including some of the most distant primordial galaxies. They have learned more about the early universe. Most of these early and distant galaxies have not yet formed stars, and are also characterized by atypical shapes, as they appear smaller and more irregular than those closer to us. This is seen as clear evidence that galaxies are formed through the merger of smaller objects. The Hubble Frontier Fields Observational Program has harnessed the power of large galaxy clusters to the full potential of the Hubble Space Telescope. The Hubble's high sensitivity and resolution allows it to observe faint and distant gravitational lenses that are difficult to detect. With ground-based telescopes, gravitational lenses are phenomena caused by extremely large masses, such as the cores of galaxies. Galaxies, or clusters of galaxies, exert their strong gravity, which distorts the space around them, and light from distant objects passing through this curved space is deflected from a straight path, as if passing through a lens. Hubble can observe in detail circular arcs shaped like bananas, one of the main effects caused by gravitational lensing, with the distorted image of the background object in the background. An important result of gravitational lensing is magnification, which allows us to observe many distant and faint objects that are otherwise invisible. Hubble takes advantage of this magnification effect to study beyond the